Welcome to the second lecture of week 2. In the previous lecture, we started with homogenization of composites. We looked at the concepts of volume and weight fractions, their relations, and we found out the equivalent density of composite. Now, to continue with micromechanics, we will now go to the effect of voids on density. So, we have seen before that while fabricating composite, there is always a chance of some voids being formed, and this void degrade the strength as well as it affects the density also, because these voids are massless, but they occupy some volume. So, with that there are concepts of two kinds of densities of composite. One is the theoretical density, that means if we assume that there is no void, then what density do we get? And there is experimental density, that means with the presence of void by experiment what density of composite do we get. So, if we assume that there is no void, then the total volume of fiber and matrix, that is considered to be the composite volume, and that is going to be weight of the composite divided by the density of the composite, and we call it rho C T. Here T denotes density. And let us say that we perform an experiment and that gives us the actual density of the composite. So, that then the volume of the composite becomes Vf plus Vm plus V void. Here V stands for volume of void. So, we have a new quantity Vv that stands for void volume. So, that volume is going to be weight of the composite, which remains same, divided by the experimentally obtained density of the composite. Now, we can find out the relations between these two. So, this has the term Vf plus Vm, which is just this. So, what we can do here is we can just in this expression we can substitute this Wc by rho Ct here, and that gives us volume of void is equal to Wc by rho Ce minus Wc divided by rho Ct. Now, we can always write this Wc as sorry. So, this is going to be volume of void. So, this Wc can be written as the volume of the composite multiplied by the experimentally obtained density of the composite, and then we have 1 by rho Ce minus 1 by rho Ct. Now, we can take this Vc in the denominator here, then we get a quantity called Vv by Vc, volume of void by volume of composite, and that is nothing but void volume fraction of void. So, like we have defined something called volume fraction of fiber, volume fraction of matrix. Similarly, we can define something called volume fraction of void, and that is going to be volume of void divided by volume of composite, with volume of composite being volume of void plus volume of matrix plus volume of fiber, and then it becomes rho Ct minus rho Ce, if we just simplify the expression, and then in the denominator we have rho Ct. Now, while defining the theoretical density, we are not including the volume of the void, whereas while defining the experimental density we are including the volume of the void. That definitely tells us that the theoretical density is going to be higher than the experimental density. So, this quantity is a positive quantity, and naturally this fraction is a positive fraction. Now, we will look into one simple problem from one of the books that we suggested by Cow. So, the problem says that there is a graphite epoxy cuboid specimen and the dimension of the specimen is A by B by C and its mass is m. It is put into a mixture of sulfuric acid and hydrogen peroxide, and after that the remaining graphite fibers have a mass of mf. So, basically by this process we are eliminating the matrix and whatever we are left with is the mass of the fiber. So, the mass of the fiber is given to us, mass of the composite is given to us and the dimensions. So, the volume of the composite is given to us. Now, what it asks from us is the volume fraction of voids in terms of these quantities and also the densities of the constituents are given to us, matrix and fiber. So, for that the approach that we can follow is, let us define the volume of the composite as V c as a summation of V m plus V f plus V m plus void volume. Now, V c, that means the volume of the composite is nothing but A B C, because it is a cuboid with dimensions A, B and C. Similarly, the volume of fiber can be defined as mass of the fiber divided by the density of the fiber, and the volume of matrix can be defined as the volume of the mass of the matrix, which is nothing but volume of fiber, mass of fiber subtracted from the mass of composite divided by the density of the composite, and we have V V separately coming here. Now, we can define the void volume fraction V V as small v v by small v c and then rearrange the terms. That gives us 1 minus 1 by V c multiplied by V f plus V m. Then we can put all the values that we have got and that gives us 1 minus 1 by A B C, 1 by A B C multiplied with V f, and V f is nothing but mass of the fiber divided by the density of the fiber plus M c minus M f, which is mass of the matrix divided by density of the matrix. So, we have got the fiber void volume fraction in terms of all these quantities here. Next, we can take another approach. With this approach, we go back to the definition that we had just now. The void volume fraction is equal to rho C t minus rho C e divided by rho C t, and rho C t is the theoretically obtained density. So, that is nothing but M f by 1 by M f by rho f plus 1 by M m by rho m. So, this is a straightforward extension of the density that we defined in terms of the individual densities and the fractions in the last class, and rho C e can be defined as M c by A B C. So, if I put all the definitions here and this definition if I put here, finally, we get the same expression that we got in the using the previous approach. Now, we will look into one more problem, and that is also from one of the books, suggested books. This problem says that we have a composite which is made of e-glass fiber and polyester resin, and it gives us the weight fraction of the fiber. So, the fiber occupies 35% weight, that means the fiber weight fraction is 0.35. It gives us the fiber density, matrix density, and it asks us to find out the fiber volume fraction and density of the composite. So, we know that the composite density is rho c is equal to 1 divided by Wf by rho f plus Wm by rho m. Now, this relation is a straightforward extension of this rho c is equal to rho f Vf plus rho m Vm, and we know Vf in terms of Wf Wm and we know Vm in terms of Wf Wm. So, with that we can write this relation. Now, again these all are capital W's, the weight fractions. So, weight fraction of fiber is known to me, that is 0.35, that is given in the problem, and density of fiber is given to me, that is 2.5 gram per milliliter. Weight fraction of matrix is nothing but 1 minus weight fraction of fiber, and that is 0.65. So, that gives us 0.65 divided by the matrix density 1. So, finally, this also has the dimension of gram per milliliter. And the result that we get is uh, 1.266. If we do the calculation, the result comes to be 1.266 gram per milliliter. And it also asks us to find out the fiber volume fraction. So, we have related the volume fractions. So, we can use that, or we can write Wf, which is given to us as Wf by Wc, small wf by small wc, and small wf is rho f by small vf, and small wc is rho c by small vc. Now, in this expression, this is known to me, this is known to me, this is known to me, and Vf by Vc is nothing but fiber volume fraction. So, we can solve for that, and that gives us the fiber volume fraction as 0.1772. This problem can be solved by an alternative approach also. So, we will do that now. So, to solve it using the alternative approach, let us say that we have composite weight as 1 gram. So, this tells me that the fiber weight is 0.35 gram and the matrix mass or matrix weight is 0.65 gram, and we know the individual densities. So, with that I can find out the fiber volume, that is nothing but fiber mass divided by fiber density, and similarly we have matrix volume, and that is nothing but matrix mass by matrix density. Then if we have to find out the fiber volume fraction from here, we can just evaluate this. So, we have got small Vf from here, we have got small Vm from here, and we can put the values, and again we can find out the fiber volume fraction, which comes to be 0.1772. And similarly, the matrix volume fraction is 1 minus Vf, and then we know that the composite density is Vf multiplied by rho f plus Vm multiplied by rho m, and we can evaluate that quantity and we can get the density of the composite, which is 1.266 gram per milliliter. So, here we assume a certain weight for the composite, and from there we find out the volumes of the constituents, and if we know that, we can get the volume fractions, and if we know the volume fractions, we can find out the composite density. So, that was about finding out the equivalent densities. Now, we will go to the approaches that we generally use for finding out the equivalent mechanical properties like elastic modulus, Poisson's ratio and so on, and also the strength parameters and many other parameters. So, there are many different approaches. One is mechanics of material based approach, and there is something called netting methods also. There are self consistent models, there are bounding techniques based on variational principles, and then we can do exact solutions also using theory of elasticity. So, instead of doing mechanics of material based solution, which is more approximate, we can go for exact solutions. There are statistical techniques, there are semi empirical models. Mori-Tanaka method is quite popular, and also there are numerical techniques. If we read this paper by Chamis, we can find out a nice review of these different approaches, but the fact is that this paper was written in 1968. So, after that there are many methods that came, like this set of methods. So, this list is not exactly what Chami lists, but still this paper is a very good paper if you want to get a good feel of or how this micromechanics developed for composite. Now, in this course we will mostly focus on mechanics of material based approach, and also parallelly we will see the results of the semi empirical models. And as far as rest of the approach is concerned, we will just take a brief overview towards the end. Now, no matter what approach we follow, we have to make some assumptions. So, these are some of the important assumptions which we generally make for micromechanics. First of all, the ply is macroscopically homogeneous. So, we assume that instead of having separate properties for matrix and fiber, we will try to have equivalent property. So, homogenization is our goal, and we assume that they are linearly elastic and generally orthotropic. So, what do we mean by orthotropic? We will see that in the next week. We also assume that the fibers are linearly elastic, that means the fiber stress strain curve looks like this, we do not account for any nonlinear effect, and the same thing we assume for matrix also, and also the fiber and matrix, they themselves are homogeneous. We also do not assume fiber and any void in the formulation, but there are ways to account for voids. We will talk about that briefly. And we assume that the bond between fiber and matrix is perfect. That means, see if I have a composite like this, if I pull it, the fiber and matrix bond is not going to break. That means, the fibers are not going to come out of the matrix. This is a very important assumption which we will need when we find out these equivalent properties. The ply is initially in a state of stress free state. So, during fabrication of composite, there are temperature variations, and that can induce some pre stress, but we assume that those pre stresses are not there. So, it is initially in a stress free state, and also the fibers are regularly spaced and aligned. So, previously also we have seen while deriving the area fractions and the volume fractions, we have assumed that the fibers are regularly spaced, the spacing S was constant, and also they are aligned, that means they are not curved. So, before we go for deriving any specific elastic modulus or Poisson ratio, let us spend some time in understanding something which is very useful, and that is called RVE, representative volume element. Actually, this is so, as the name suggests, it is a volume which represent the behavior of the composite. So, this is the composite under study, and let us say that there are fibers oriented in this direction. Now, while studying, we do not take the entire assembly of fiber composite, rather we take a small part of the composite and study that. So, let us say that we are taking a small part of it, which consists of one or few fibers and matrix, and let us take a small volume out of it, and that small volume is called representative volume element. So, an RVE in a magnified form can look like this. So, we have a fiber here, we can see the cross section in the matrix. Now, we can further idealize this diagram. So, we looked at small volume here which represents the composite, and then we are just seeing the magnified view here, and then we can further idealize it, and we can say that whatever the shape of the fiber is, let us for the sake of understanding, let us give it a shape like this, so that this area and this area are same. So, although in the drawing they may not look same, but this is also F and this is also F. Again, for the sake of simplicity, we can further make an assumption. So, we are just going assumptions one after another. The next assumption we can make is that as far as the strength of material based approach is concerned, we shift the entire fiber area to one side and the matrix area to one side. So, this is fiber and this is matrix. Now, although in this drawing it may seem that the fiber area is less than the matrix area, but that is not a requirement. In fact, in most of the cases fiber area is much higher than the matrix area. And if we see this in 2 dimension, that means if we view this entire thing from the top, it can simply look like this. So, we have fiber in one side and matrix in one side. Now, in most of the derivations which are to follow, we will draw this diagram. That would simply mean this idealized thing, that we had a composite, we took out an RVE and then we idealize the fiber volume and matrix volume in 2 sides, and we are just looking at the same thing from the top. So, now we will find out the longitudinal modulus. Longitudinal modulus. Now, we had this idealized diagram with fiber being one side and matrix being at the other side, and let us say that this direction is 1 and this direction is 2. Now, one thing to note is that although in the previous diagram we showed that the fiber is oriented in this diagram, and this fiber orientation is almost parallel with the edge of the composite, but that is not always a requirement. This fiber can be oriented in some inclined direction also. In that case, we have to talk about 2 different directions. One is direction 1, which is the fiber alignment direction, and one is direction x, which is the direction of the edge of the composite ply or composite laminate. So, for example, if our composite ply has fibers oriented in this direction, then we could have taken on an RV which looks like this, So, this is direction 1, that means direction along the fiber orientation, and this is direction 2, the transverse direction perpendicular to one direction, and we could have defined a direction x and y, which is a global direction, just to show the ply. In fact, later on we will have to do some transformation between direction 1, 2 and x, y, we will see that later. As of now, just let us focus on direction 1, 2 and the properties along the fiber direction and the perpendicular direction. Now, to find out the longitudinal modulus, what we assume that this fiber is under applied load along direction 1, say this load is P. Now, under the application of this load, this is going to deform in this fashion. So, there is going to be extension in direction 1, and due to the Poisson's effect there is going to be contraction in direction 2. But when this happens, because we have assumed that there is perfect bond between fiber and matrix, the extension of fiber part and the matrix part has to be same. If we look at here, the fiber has to, if we look at here, the fiber has to, whatever the extension of the fiber is along this direction, the same extension of the matrix is along this direction. If I look at this, in direction 1, the fiber and matrix extension is same, because they are not supposed to detach from each other. That is one of the important assumptions that we made. If that is so, then we can say that the strain in fiber and strain in matrix is also same. So, strain along direction 1 in fiber is going to be strain along direction 1 in matrix, and we can call it a quantity epsilon 1. If that is the case, then the stress in fiber along direction 1 is going to be the elastic modulus of the fiber along direction 1 multiplied by epsilon 1. Similarly, stress in matrix along direction 1 is going to be same as elastic modulus of matrix multiplied by the strain. Now, matrix are isotropic. So, they are elastic moduli along direction 1 and 2 are same, that is why we are not using any suffix 1, 2 like that, but fibers can have different Young's modulus in direction 1 and 2. So, that is why we are using a suffix 1 here. If that is the case, then the total force taken by the fiber is total force along direction 1 taken by the fiber is sigma 1f multiplied by AF, that means area of the fiber. So, area of the fiber part at this face, and similarly the load carried by matrix and along direction 1 is sigma 1 m multiplied by A m. Then if we write the total load is sigma 1 f multiplied by A f plus sigma 1 m multiplied by A m, that is the total load, and that total load is nothing but what we are applying here. Now, we will bring a concept of equivalent stress in fiber and matrix. We have seen that the stress in fiber and matrix are different, but now we bring in a quantity called equivalent stress, and then from that equivalent stress we will define something called equivalent elastic modulus. So, let us say that there is an averaged out stress sigma acting on let us say that we have an averaged out stress sigma acting here along direction 1. So, with that sigma we can write or we can call it sigma 1 because it is in direction 1. So, sigma 1 multiplied by AM plus F is the total force. So, the total force that we obtained by multiplying the total area with the averaged out stress is same as P, and that is same as the individual force taken by the fiber and the matrix. Now, sigma 1 F as we have defined is nothing but E 1 F multiplied by epsilon 1 into F plus E 1 M multiplied by epsilon 1 multiplied by A M, and then we have sigma 1. So, sigma 1 can be written as E 1 multiplied by epsilon 1. So, now here we are bringing in a term called E 1, and that is our equivalent Young modulus of the composite along direction 1, equivalent elastic modulus of the composite along direction 1, and that is the quantity that we want to find out. Now, E 1 is same in all the terms, and so that goes away, and we can take this A m plus A f in the denominator here, and then we get terms like A m by A m plus F, and that is nothing but fiber volume fraction V f, and here we get A m by A m plus F, that is nothing but fiber volume fraction V m. So, with that we can write V f multiplied by E 1 F plus V m multiplied by E m. So, the elastic modulus of the composite along direction 1 is a weighted combination of the individual elastic modulus of matrix and fiber, where the weight factors are their respective volume fractions. Now, as we have seen that this makes some assumptions, and one important assumption is that it has to be aligned. So, if there is some misalignment, for that a fiber alignment correction factor was K was proposed by Whitney and Riley in this paper. So, the interested learners can refer to this paper and get more idea about it, and this says that E 1 can be written as a correction factor K multiplied by V f into E 1 f plus V m multiplied by E m. So, depending on the nature of misalignment, K can be different. So, with that I would like to conclude this lecture. In the next lecture we will derive other mechanical properties like transverse modulus, shear modulus and so on. Thank you.